and welcome to another session of Physics by Cloud Tutors, powered by Connecting the Dots, a program to help grade 10 students to prepare for their board examinations. Today, we will take up the topic electricity. So, electricity as a chapter holds a weightage of around 8 to 10 marks, of which there may be questions of 1 mark, 2 marks, 3 and 5 markers. So let's look at a few details on these type of questions, or what kind of questions can you expect in your question paper. So as you can see on the screen, 1 or 2 markers are usually based on the definitions or simple equations of electric current or voltage or any other simple circuital problems. Whereas your long answers are usually based on combination of resistors, wherein you will learn parallel and series resistors in further sessions, and it can be a combination of 3 marks and 2 markers as well. So with this brief information of your examination point of view, let's look at this chapter's mind map. So again, this is briefly what we have put up here. So electricity as a chapter can be divided into 2 sections, where you will learn what is electricity or what is electric current, which is again further split into electric charges and different topics related to it. Another section of it, furthermore, once you learn about electric current and how does it work, we will be looking at few other topics which is related to electric current, voltage, electric potential or potential difference, resistors, different combination of resistors that are used in different kind of circuits, and also finally we will be learning about heating effect of electric current and also about electric power and how electric power is related to the electricity that we use in our daily lives. Alright, so without further ado, let's get started with today's session. So electricity as an entity or as an element we all use in our daily lives, as and when we get up in the morning right to we go to bed. So how do we get this electricity and what is this electricity? Before getting into this concept, now let's understand in general what do we mean by current. So we use this word current in our lives for, do we have electric power or not? We have the current today, we do not have the current today. But current in general means flow of particles. It could be any particles. For example, as you can see on the screen, flow of water particles is called as water current. Flow of air molecules or air particles is called as wind as such. So what do we mean by electric current? Electric current is nothing but flow of electric charges. So in order to understand electric current better and electricity better, let's first understand what do we mean by electric charges. Electric charges are a property of any kind of object or a particle due to which it experiences an electric force, or it could also exert an electric force onto another particle or an object due to this particular property. So electric charges are of usually 2 types or 2 kinds. One is positive, another is negative electric charge. So the fundamental property of an electric charge is like charges repel each other and unlike charges attract each other. So as you can see, when I place a positive charge along with the positive charge, there will be a repulsion force or force of repulsion that you see when you place 2 like charges together. This is very similar to placing 2 like poles, that is north and north pole of a magnet together, of 2 magnets together. When you see that they actually repel away, right? So even here it is very similar, but here we are talking about electric charges, where like charges repel each other and unlike charges attract each other. So with this fundamental property, let's understand what is Coulomb. Coulomb is nothing but the SI unit of electric charges. This is the unit in which we measure we measure the electric charges. Now, when we write 1 coulomb or 1 coulomb of charge, it is quite a large amount of charge. So, if at all we'll have to have any other form of units for this particular entity, that is electric charge, we also have something called as 1 millicoulomb, which is written as 1 small m and c, and this is equal to 1 coulomb divided by 1,000. So this I can write it as 1 into 10 raised to minus 3 coulombs. There is also something called as a microcoulomb, which is again 1 coulomb divided by 1 followed by 6 zeros. So that I can write it as 1 microcoulomb. So this is a symbol called as mu, which is a denotion for anything which is preceding the unit that is equal to a micro unit. Okay. So 1 microcoulomb is equal to 1 into 10 raised to minus 6 coulombs. So as you have understood now, there are two kinds of electric charges. One is positive and another is negative. And electric charges are measured using a unit called as coulomb. It is named after a physicist who actually studied electric charges and static electricity extensively. Alright, so with this brief understanding, let's furthermore understand where did we get these electric charges from. There should be some origin of these charges, right? So where are these charges coming from? How do we know it is positive and negative? How do we know it is they are repelling each other when two like charges are kept together, and two unlike charges when kept together, there will be a force of attraction, right? So when I say force of attraction, we are talking about the electric force here. Now, when we look at a structure of the atom, what is atom made up of? We all know that by now. You would have studied this in chemistry. An atom is made up of protons, neutrons, which makes the nucleus, which is the center of the atom, and there are negative electrons revolving around this nucleus. Now, what we need to understand here about the structure of the atom, or these particles, that is electrons, protons and neutrons, is that, as you can see it on the screen, negatively charged electrons revolve around the positively charged nucleus. So why have I written it as positively charged nucleus? Because the nucleus, which is at the center of the atom, contains positively charged protons and neutral neutrons. The neutrons as particles, they are not electrically charged anyways. They are electrically neutral. That is, they do not have any kind of charges. So since the nucleus contains both protons and neutrons, and the only charged particles over there are protons, which are positively charged, the nucleus as a whole becomes positive entity or positively charged entity. And hence, what happens in an atom is, or how is an atom stable, as you would have studied in chemistry, because of the electrostatic force of attraction between the electrons, negative electrons, and the positive nucleus, there is a balance, right? So if we remove an electron, what happens to the atom? The atom becomes positive ion, right? How does this happen? Think about it. Now, when an atom is in stable state, the number of, or the amount of positive charge and amount of negative charge are balancing each other, right? Now, when there is an imbalance in this particular amount of charges, now we cannot do anything to the number of protons because they are inside the nucleus, and it is very, very difficult to remove or remove the protons or neutrons from the nucleus. That is another matter for another day. So first, let's just say that it is very, very difficult, or it is almost impossible to remove the protons from nucleus to reduce the amount of charges as such. So during a stable state, or when an atom is in stable state, both the amount of positive and negative charges are balanced out. When we remove a free electron from an atom, what happens is the amount of negative charge comes down and the amount of positive charge remains the same. But as an atom, now the atom holds more of a positive charge and becomes a positive ion, which is called as a cation. Now, what happens when an atom becomes an anion, which is a negatively charged atom? There will be an addition of extra number of electrons, or one extra electron, which again creates an imbalance between the amount of positive charge and the negative charge in an atom. So as you can see here, there will be no difference in the number of positive charges, that is protons, because they are inside the nucleus, which is very, very difficult to divide, or very, very difficult to open as such. Okay. Now, you need to understand the fact, whenever we are talking about the flow of charges in terms of electric current, we are only talking about the electrons, which are negatively charged. So please do not be under the impression or under the misconception that if we are saying a particular object is positively charged, it contains more protons. No, it is not that there will be no difference or no increase or decrease in the number of protons, but there will be excess or deficit number of electrons on that particular object. How is this? If a particular object is, if we say it is positively charged, it just means that it lost a few number of electrons, hence the amount of positive charges are more than that of the negative charge. If we say a particular object has a negative charge, it just means that it has excess number of electrons. That's all it is. There will be no difference, or we cannot actually increase or decrease the number of protons present in an atom and hence in an entire object. Alright, so with this understanding, let's move on and look at the next topic, that is charge on an electron and a proton. So as we have already discussed, the SI unit, or the unit in which we measure electric charge, is coulombs. So how much is the electric charge possessed by an electron or a proton? It is exactly the same. Only difference is the polarity. By polarity, I mean if the particle is negative or positively charged. So as you can see it on the screen, an electron has a negative 1.6 into 10 raised to minus 19 coulombs as its electric charge. And mind you, it is a negative charge. So the exact magnitude, or it is the exact amount of electric charge possessed by the proton also, but the proton has a positive polarity. Alright. Now, with this, let's understand another concept of quantization of charges. Now, by this, what do I mean? So, if I say a particular object has 5 coulomb of charge or 1 coulomb of charge, I can most definitely measure this in terms of number of electrons. Why is this? Because whenever I say a particular object or a particle is negatively charged or positively charged, by that we mean we can, as we have already discussed, we can only increase or decrease the number of electrons which are negative charges present in a particular object, and we cannot actually increase or vary the number of protons which is inside the nucleus, right? So anything and everything which possesses an electric charge basically can be put it across or can be measured in terms of number of electrons. So what we can say here is the amount of charge possessed by an electron is the fundamental amount of charge possessed by a particular object. So multiples of this, or multiples of an electron's charge, can be put it or can be used to measure the amount of total charge possessed by a particular given object. So if Q is the amount of charge possessed by an object, this can be written in terms of or multiples of the amount of charge of that is possessed by an electron, which is denoted by E. And we have already seen E is equal to 1.6 into 10 raised to minus 19 coulombs here. So if Q is the amount of electric charge possessed by an object, I can write it as any number, that is, we are quantifying the amount of charge possessed by an object in terms of number of electrons on it, right? Number of why do we do this? Because electrons charge is the fundamental amount of electric charge a particular object can contain. So how many times of this electric charge possessed by an electron is on the particular object is what we are calling it as quantization of charges. So this entire object, if a particular object has an electric charge of Q coulombs, this can be written in terms of multiples of the electron charge, which is N into E, where N is a number, whole number. Okay. Now here we will not, just because we are calculating the amount of charge contained by a particular object, we will not be considering the negative or positive polarity here. We are just sticking with the magnitude of the electron charge, that is E is equal to 1.6 into 10 raised to minus 19 coulombs. Alright, so how do we quantify a particular object's electric charge? We can quantify by measuring it in terms of number of electrons that actually takes to make such a big amount of electric charge. So we will look at few examples, then you will have a better understanding on this concept. Okay. Now let's just look at first example, that is how many electrons make 1 coulomb of charge. So if I say a particular object has Q coulombs of charge, how many electrons does it take to make Q coulomb of charges? As we have written the formula already, Q is equal to N into E. So it may take any N number of electrons to make a charge of Q coulombs. So here in this example, Q is equal to 1 coulomb, right? Now let's calculate and check how many number of electrons is required to make 1 coulomb of charge. So with this quantization equation, that is Q is equal to N into E, where Q is the amount of charge possessed by an object, N is the number of electrons, and E is the electron charge or charge in an electron. Okay. So since we know Q is equal to 1 coulomb, let's substitute and find out the value of N here. And we also know E is equal to 1.6 into 10 raised to minus 19 coulombs. Correct? So let's substitute it. Q is equal to N into E. Therefore, what are we supposed to calculate? We know these two quantities, right? Any equation that contains 3 quantities, if you know 2 of them, you can easily calculate the third one, right? So that's what we are doing here. Now we have to calculate the quantity N. How many number of electrons make 1 coulomb of charge, right? So N is equal to, if I transpose E on the other side, what do I get? I get Q divided by E. Let's substitute the values here. 1 coulomb is the amount of charge here, that is the value of Q. And how much is the value of E? 1.6 into 10 raised to minus 19. So if I simplify this, what do I do? 1 divided by, here is a decimal point, so I'll get rid of the decimal point. I get 16 here, and here what do I get? I removed a decimal point from this particular quantity, so I get here 10 raised to minus 20. So if I send 10 raised to minus 20 upstairs, that is to the numerator, what do I get? N is equal to 1 divided by 16 into 10 raised to minus plus 20. So this is a formula that you might have learnt in your exponents chapter in your mathematics syllabus. So that is 1 divided by x raised to a is equal to x raised to minus a. When you send a particular digit with a power to the numerator, the power becomes negative, or vice versa, right? So now I have plus 20 as the power of 10. So if I simplify this, I get a number which is like 6.25 into 10 raised to plus 18 electrons. Now I cannot write the number of electrons in terms of decimals, right? So this will be 625. I remove the decimal onto the, or I move it 2 digits after the point here, or I move the point here or the decimal point here. So I get 625 into 10 raised to how much? I will get it as 10 raised to 16 electrons. So these are the number of electrons present in 1 coulomb of charge, which is a huge number, right? So because electron possesses such a less amount of charge, which is very, very minute, which is equal to 1.6 into 10 raised to minus 19 coulombs, it takes a very large number of electrons to make 1 coulomb of charge. All right, so I hope you all have understood what do we mean by electric charge, and where do we get these electric charges from, what are positive charges or what are negative charges, what are the fundamental properties of these charges. With this basic understanding, let's move ahead and understand what is electric current. So electric current, by current, as we have stated in the beginning of the session, electric current or current in general is nothing but flow of particles. So in particular, what is electric current? Electric current is nothing but rate of flow of electric charges, and it is measured in amperes. Okay, so how do we actually do this? As you can see here in the picture, if we take a copper wire, which is a conductor, we will come to what is a conductor and insulator in a while. So if we zoom into a copper wire and which is connected in an electric circuit, and see what is happening over there, you see that the free electrons which are present in copper atoms are flowing, right? So this rate of flow of electrons through a conductor is called as electric current, and it is measured in amperes. Okay, now what are conductors and insulators? For this, we will look at a small demonstration in a few minutes. Before that, let's understand what is a conductor and what is an insulator. A conductor is a material which allows the electrons to, or which allows the passing of electric current through itself. Now, why does this happen? Because because conductors are the materials which have a lot of free electrons. I'm sure you would have learned what are free electrons or valence electrons in your chemistry syllabus, right? So whichever materials or whichever elements have a lot of free electrons, they allow the passing of electric current through them readily. So such materials are called as conductors, and the materials which do not allow this process to happen are called as insulators. Insulators, unlike conductors, do not have many number of valence electrons or free electrons, or they do not have them at all. So this basic difference makes the material basically become an insulator or a conductor. So if it is a conductor, it allows the passing of electrons or electricity to pass through it readily. If it's an insulator, it does not allow the electric current to pass through it. So let's look at a small demonstration how a conductor works and how an insulator works using a small and simple electric circuit setup. So this is a simple setup to show the properties of a conductor and an insulator. So as you can see here, it is a simple circuit which is built using a battery which acts as a voltage source, and there are connecting wires here, and there is a lamp to show if there is a flow of electric current through the circuit or not. So as you can see here, there is a gap between the circuit, or the circuit is not complete here. So as in when we complete this circuit, the bulb should start glowing. That shows you there is a flow of electric current, or there is a flow of electric charges. Those are electrons here. So here in this experiment, what we are going to do is test a few materials which show the properties of a conductor and show the properties of an insulator. So this is again this is to show you if we complete this circuit, the bulb obviously glows, right? So this basically tells you that there is a flow of electrons, or there is electricity flowing through it, electric current flowing through it, right? So I have a few materials here, or few different kinds of materials here. As you can see, I have a wooden piece, I have a plastic straw, I have aluminium strip and a copper strip, and also a silver chain. So let's see what makes the bulb glow, or what does it. So if it is a conductor, conductors are the ones which allow the electrons to pass through them, right? So in that case, what happens is the bulb should glow. So let's see what copper does. As you can see here, when I make the connection, or when I complete the circuit using this copper strip, you see that the bulb is glowing. This clearly shows you that copper is a conductor, which allows the electrons or electric current to pass through it readily. Let's check what aluminium does. There is an aluminium strip, as you can see here. So when I make the connection using the aluminium strip, there you go. You see that the bulb glows. So aluminium is also a conductor. Let's check if the wood piece does the same. I have completed the connection using a wooden piece, but as you can clearly see, the bulb doesn't glow. It shows you that wooden piece, or any kind of wood, obviously is an insulator. An insulator, as you all know, is a material which does not allow the electrons to, or electric current to pass through them readily. Now let's see what silver does. So when I complete the connection using this silver chain, you see that the bulb glows, right? So silver is also a conductor. Let's check what plastic does. It's a plastic straw, normal straw that we used to get. Nowadays we don't, because we have switched to paper straws, right? So as you can see, I have completed the connection, or completed the circuit using this plastic straw, but as you can see here, the bulb doesn't glow, which shows you clearly that there is no flow of electrons through the circuit even though it is complete, because we are using an insulator in between the circuit to complete the connection, which does not allow any kind of electric current to pass through them, right? So these are the few materials, as you can see, and we already know that we differentiated which are the conductors and which are the insulators here, right? So the wood piece and the plastic straw which we used to complete the connection or complete the circuit did not allow the electric current to pass through them, whereas the aluminium strip, the copper and the silver chain definitely did the job well. It glows, right? So these three are the conductors and these two are the insulators. So now that we have looked at the demo, I'm sure you would have understood differences between insulators and conductors very well. Now, how do we measure this electric current? As we have already seen, electric current is measured in terms of amperes. Okay, this is also is named after or named in honor of a French physicist who studied electric current very extensively, and the unit is ampere. Again, to make it appropriate, we have milliamperes, microamperes, which is again can be written as 1 milliampere, as we have done it for the charges. 1 milliampere is equal to 1 into 10 raised to minus 3 amperes, and 1 microampere is equal to 1 into 10 raised to minus 6 amperes. So these prefixes, that is micro or milli, will tell you how much is the 10 raised to factor that you have to multiply. So please be careful during your examinations. If your question says it is some amount of milliamperes, then you will definitely have to use this conversion factor. If it is some amount of millicoulombs, even then you will have to multiply it by 10 raised to minus 3. Please do not just take the number and do your problem as such. Okay. Now, what do we mean by electric current? By definition, electric current is the rate of flow of charges, or as you can see here, it can be given by the equation I is equal to Q by T, where Q is the amount of charge that is flowing through the conductor per unit time. So we can write the equation as I is equal to Q divided by T, where T is measured in seconds and Q is measured in coulomb and I is measured in amperes, denoted by capital A. Alright, so this is how we measure, or this is how we give the electric current is given in the form of an equation. Now this is also an equation which contains 3 quantities. If 2 quantities are given, you can easily calculate the third one. Let's look at few examples on the later stage of this session to understand this better. Now, if at all we are asked to define 1 ampere, how much is 1 ampere of current, then you will have to define it in this way. Or what do we mean by 1 ampere of current? You can say that whenever there is a flow of 1 coulomb of charge through a conductor per unit time, then the amount of current flowing through that particular conductor is said to be 1 ampere. So how do we define it? 1 ampere is the current constituted by a flow of 1 coulomb of charge per second or per unit time. Alright, when I say unit time or unit charge, it just means 1 coulomb or 1 second. Alright, so this is how we define 1 ampere of electric current. So this could be a 1 marker, or this could be a 2 marker combined with some other equation, some other numerical which is based on electric current equation or charge equation. Alright, now with this basic understanding, let's understand how a particular amount of current through a circuit is measured in reality, or in practical, or in practice I mean. Now, as you can see here, we have a simple circuit, and the instrument or the component that we use to measure the amount of current through a particular circuit is called as an ammeter. Now, as you can see here, there is a source, right? We need some kind of source through which actually supplies the required amount of energy that gets the electrons going, right? So this particular black line shows you the kind of electric circuit, and here is a bulb. It's a very simple setup, as you have seen in the demo, where the bulb usually bulb glowed as in when we completed the circuit using conductors, right? That is what a simple setup here is, but there is an extra component, that is the ammeter. Now, what is an ammeter? Ammeter is a component which is connected in an electric circuit to measure the amount of current flowing through it. As you can see here in the circuit, ammeter is always connected in series with the in the circuit where we have to measure the amount of current. Now, why is this? Because as we stated, ammeter is an instrument which measures the amount of electric current flowing through a particular part of conductor or in a circuit. Now, if we connect it differently, if we connect the ammeter in parallel, what happens? The amount of current, as you can see, will be flowing through this branch of circuit as well, which is not the complete amount of current which will be flowing through the actual circuit. So if we connect the ammeter differently, that is other than the series, what happens is it will not be able to measure the entire flow of current that flows through the entire circuit. Hence, ammeter is always connected in series in which we'll have in a circuit in which we have to measure the electric current. All right, or with any other component through which we wish to measure the electric current flowing through it. So, and also we need to understand another fact about ammeter is that ammeter needs to have very little resistance. Resistance in detail we will learn in further sessions, but to briefly tell you, resistance as the word states or as the English meaning goes, it is nothing but a kind of opposition that is posed by anything or opposed by a circuital component or anything that is present in the circuit to the flow of electric charges. Okay, so if at all ammeter itself poses a lot of resistance or an opposition, what happens? Because it has to measure all the current flowing through a particular component which is connected in series with it, if the ammeter has a lot of opposition to the current, the current won't flow through it, or a very little current flows through it, and hence it won't be able to give you the correct reading, or it won't be able to show you the correct measurement, right? So the ammeter has to have very minimum resistance, or ideally it has to have zero resistance. All right, so two things that we need to understand and remember here: ammeter is an instrument which is connected in series with the component or in a circuit where the current needs to be measured, and ammeter needs to have very minimum amount of resistance, or ideally zero resistance. All right, this is how we measure electric current in a given circuit. Now, how do we calculate the amount of electric current using the given amount of information? Or here, as you can see, we have examples. So let's look at one of these examples. If 4 coulombs of electric charge flows through a conductor in 1 second, then how do we calculate the amount of electric current flowing through it? As we all have seen already, what is the equation for electric current? Electric current is denoted by capital I, and it is measured in amperes, right? Electric current I is given by electric charge flowing through the conductor per unit time, right? So I is equal to Q divided by T. What is the data that we have here? We have been given the charge and we've been given the time here. So I is equal to, let's substitute the value. Q is 4 coulombs and T is equal to 1 second. So 4 divided by 1 gives me 4 amperes. Easy, right? So even if you have been, if you were given the electric current value and if you've been given the charge, you can also calculate the number of or amount of time for which these electric charges flow through this particular conductor to constitute a certain amount of current, right? So this is again an equation which contains 3 quantities, wherein you've been given 2 quantities, you will have to calculate the third one. So it is quite simple and very straightforward. The second one as such, again, I is equal to Q divided by T. What is the value of electric charge here? It is 6 coulomb, and the amount of time for which this amount of charge flows through the conductor is again 1 second. So here is a very simple calculation and your answer is 6 amperes. And here the third one, there is a slight change, that is again a very simple and straightforward thing. I is equal to Q divided by T. The value of Q is 6 coulombs, and amount of time for which it flows is 2 seconds. 6 divided by 2 gives you 3 amperes. Alright, very simple and straightforward, and this could be a 1-marker question. Now, whenever we say there is a flow of electric charges, there should be something that is acting on these charges because it is flowing, right? If you look at a bucket of water, obviously you will see that the water is not going anywhere. So if you have to make the water move, you need to put lift the bucket and pour it, or make a hole and pull the water out of the bucket. So basically you are doing some kind of activity or some amount of work in order to pull the water particles out of this bucket, right? So it does not actually just the water does not actually flow as it is if it is kept on a normal ground, or if it is kept still. Correct? So this goes the same, or it goes the same for electric charges also. If a particular object is electrically charged, until and unless there is some amount of, or some entity which pulls them, or which applies force onto the charges and pulls them onto one of the sides, the electric charges do not get going or do not actually flow, and hence there will be no electric current constituted through that conductor, or in practice we say it is in a circuit, right? So there should be some kind of quantity or some entity that does this job, right? So the amount of work done on the charges on a given positive unit charge to make it move from one place to another in a given circuit is called as potential difference. What is this potential difference? Potential difference is that amount of work that needs to be done on a given unit positive charge to move it from one point to another in a given conductor. All right. So how is this important? Because we have to get the charges moving in order to constitute an electric current, we need this amount of work to be done. And this amount of work done on a unit positive charge to move from one point to another in a given electric circuit or in a given conductor is called as electric potential difference. In normal terms or layman terms, we call it as voltage. Okay. So what makes electric charges flow? It is basically the potential difference across the conductor. All right. So the analogy of water flowing from a higher level to a lower level basically tells you that no amount of particles or none of the particles, be it water or electric charges, will flow if there is no difference in the levels. Correct? Here there is pressure difference between the, or level of difference between the water buckets that you see on the screen. So in order to make the electric charges flow, we need to create an electric pressure difference, and this amount of work that basically needs to be done on a charge to go from a higher to lower level is called as the potential difference, or this difference in electric pressure is the potential difference, or it is in general called as voltage. Okay, so the electrons move only if there is a difference of electric pressure, and this is called as the potential difference, or in general terms it is called as voltage. And this voltage or potential difference is measured in terms of volts, or SI unit of voltage or potential difference is volts. So as you can see it here in the diagram or on the screen, you see that if there is no difference in the levels or the electric pressure, there will be no flow of electrons. Correct? It is exactly the same as you see that if there is no difference in the levels of water between two buckets, or if it is at the same levels, there will be no flow or exchange of particles as such. Correct? So in order to do so, what do we need to do? We need to create a pressure difference. Here in terms of electrons or electricity, we call this as potential difference. So this is what exactly happens when a battery is connected across a conductor. Until then, what will be the electrons doing? Electrons will not be flowing. Electrons are basically the electric charges which constitute an electric current when they start moving through a conductor, right? So if at all there will be no potential difference or difference in the electric pressure, there will be no amount of work in moving a charge from one point to another through a conductor, and hence there will be no electric current through that conductor. So in order to make the electrons flow, what do we need? We need to create a potential difference, or we need to give it voltage. Alright. Now how do we define potential difference? As we have already seen it, electric potential difference between 2 points in an electric circuit is the amount of work done to move a unit charge from one point to another. The SI unit of electric potential difference, both of them are measured in volts. Now what is the difference between electric potential and potential difference? It is very simple. Electric potential is in terms of a larger distance, and we are not talking about the difference between 2 points which are very, very closer in a circuit. Whereas in potential difference is basically within a circuit. Alright, so what do we mean by electric potential? Electric potential is also the amount of work done on a unit charge to bring it from a point of infinity, from a larger distance to a given point in a circuit. Whereas potential difference is the amount of work that needs to be done on a unit charge while moving it from one point to another within a circuit. Alright, both of them are measured in volts, or SI unit of both electric potential and potential difference is volts. Now, how do we measure this voltage or potential difference? As we have similar to ammeter, which is a component which needs to be connected in a circuit in order to measure the electric current, we have something called as voltmeter. Now, the difference between voltmeter and an ammeter, one obvious difference is that ammeter is a component which is used to measure the electric current, whereas voltmeter is a component which is used to measure the electric potential difference. Now, ammeter needs to be connected in series because the current has to pass through it in order to give it a reading, or in order to get it measured, right? Now, potential difference is between 2 points in a circuit. So the voltmeter, when we have to measure the potential difference between across a conductor or between 2 points in a conductor, we will have to connect it parallelly or across the circuit, wherein ammeter has to be connected in series with the component through which the current needs to be measured, right? So voltmeter, it has to be connected in parallel or across the points. Say for example, these are the 2 points that we need to measure the voltage across or potential difference across. So what do? If I connect the voltmeter here somewhere, what happens? The voltmeter will give me the potential difference between these 2 points, that is A and B here. But that is the only potential difference I'm going to get. If at all I need to measure the potential difference across the circuit, I need to connect it across the battery or parallel to the battery's terminals so that I get the correct voltage, right? So voltmeter has to be connected in parallel or across the component across which we need to measure the potential difference. And another important thing is voltmeter needs to have maximum amount of resistance. Why is this? Because it should not allow any amount of, or it should allow very minimum amount of electric current to pass through them, because we will be using normal wires to connect, make the parallel connection of the voltmeter across a given circuit or a given component in the circuit, right? So it is but obvious that the electric current will pass through these conducting wires. But if at all the voltmeter does not have good amount of resistance, what happens? The current will be branching out, the current will be divided, and it will also flow through the voltmeter, which again makes the ammeter reading different, right? So in order to avoid this, what we need to do is, or what we need to bear in our minds is that a given voltmeter needs to have maximum amount of resistance, and it needs to be connected in parallel or across a given component around which across which we are measuring the potential difference. All right. So two things that we have to remember about ammeter and voltmeter each is that ammeter needs to be connected in series, and it should have very minimum amount of resistance, whereas voltmeter needs to be connected in parallel and it should have maximum amount of resistance. All right. Now coming to the measurement of this voltage, or the equation of potential difference. As we know, by definition, potential difference is the amount of work done to move a unit charge from one point to another, right? So how do we write it in the form of an equation? As you can see here, it is work done per unit charge. So in the form of equation, we write it as capital V is equal to work done is given by W, that is capital W, divided by amount of charge Q, while W is measured in joules and Q is measured in coulombs. All right. So, and V, SI unit of V is again volts. All right. Now how do we define 1 volt of potential difference between 2 points? 1 volt of potential difference, or the potential difference between any given 2 points of a conductor is said to be 1 volt if the amount of work done, or if we do 1 joule of work to move a unit charge from one point to another in a given circuit or across a conductor. All right. So this definition of volt can be asked for 1 marker, or you could be asked a numerical based question on this given equation, that is equation of potential difference given by V is equal to W by Q. All right. So please remember the SI units properly. SI unit of work is joules and SI unit of charge is coulombs. If either of them are not in their SI units, for example, if the charge is given in terms of millicoulomb, you need to convert it into coulombs. That is, how do you do that? If, for example, the amount of charge given is 5 millicoulombs, you need to multiply the 5 number into 10 raised to minus 3. Only then you will get it in terms of coulombs only. All right. Please remember that and do not forget your conversion factors. All right. Now with this information, let's look at few practice questions. So this appeared in 2 of your previous year's examinations, as you can see, to 2005 and 2012. Again, it's a very straightforward question. What is it? Define 1 volt of electric potential. What is the SI unit of electric potential? So we have studied it just now. What do we mean by electric potential and potential difference? Both are slightly different, right? How do we define electric potential? Electric potential is the amount of work done on a unit charge to bring it from a point of infinity to a given known point is called as electric potential. What is the SI unit of electric potential? It is again volts. Okay, so this could be a 1 marker, or sometimes if they are generous, it could be a 2 marker. Next question, again, as you can see, it is a very similar question, but it is again very repetitive as well. So what do you mean by potential difference between 2 points in an electric circuit? Again, the answer is very simple, as we have defined what do we mean by electric potential as well as potential difference. It is very easy. What is electric potential difference? The amount of work done on a unit charge to bring it from one point to another within a circuit or along a conductor. This is your electric potential difference or voltage. Alright, so this is also 1 marker. Please write your definitions with the keywords. Do not forget your keywords, which are very, very important when you write your examinations. Okay. Next one. If you pass 500 milliamperes of current through a bulb, how many electrons will pass through it in 10 seconds? Now, let's see what have they given us. It's very important that you write the given data first. What have we been given? We have been given I, that is the current, 500 milliampere. It is not an SI unit, so we need to convert this 500 into 10 raised to minus 3 amperes. And we have been given the time, 10 seconds, correct? What are we supposed to calculate? We need to calculate the number of electrons, right? It's a slightly tricky question. You need to go through two steps here, right? In order to understand or in order to calculate number of electrons, we need electric charge. So how do we do that? Using equation of current. I is equal to Q by T. Therefore, Q is equal to I into T. You get Q is equal to 500 into 10 raised to minus 3 into 10 seconds. So how much do I get? I get Q is equal to 5 coulombs. Now that we have charge, we can always calculate the number of electrons using this equation, that is quantization equation. Q is equal to N into E, where E is nothing but electron charge, that is 1.6 into minus 19 coulombs, and N is the number of electrons present in 5 coulomb of charge in this case. So with these few practice questions and the concept of electric charge, electric current, potential and potential difference, we come to end of today's session. Let's meet up in next session. Thank you.